Right, I'm sorry for disturbing you. We would like to have a coffee break now, but we're a little bit behind the schedule. So postpone everything. I try to speed up a little bit. But that's our numbers. I'd like to introduce my co-authors. It's Gerhard and Willy. We are from Boku University, University of Natural Resources and Life Sciences in Vienna. It's the agricultural university there. And today I'd like to present some results of my PhD findings. It's a little bit, these findings are now 1.5 years old, so it's not the latest, but anyway, it's still interesting, I think. What I would like to draw your attention at is hydraulic properties, and first I'd like to start with a small introduction. When we have a look at the soil, we know that it's at the interface between the atmosphere, the groundwater below, and we call it the vado zone. You all know it's part of the water cycle, and we have many different aspects or impacts that change the pore system. And in this talk, I'd like to focus more on the structural part of the pore system, because in terms of changes that are affected by soil cultivation, like different tillage treatments, but also effects like soil compaction, changes due to biological activity, we may assume that most of the impact will be in the structural part, in the larger pores, and not in changes in, let's say, the silt or clay content, whatever. So that's the first introduction, and the main question that was that we were wondering is how soil hydraulic properties change with time. And you all know that when we apply a Hydrus software, for instance, we set these properties to be constant. We go to the field or use laboratory results, determine hydraulic properties once for our study, and then we assume that there are no changes. And of course, there are some studies that found there must be some changes of hydraulic properties. And we were wondering how different soil cultivations, this means different tillage treatments, affect hydraulic properties, and we assumed that there must be changes over time. So we wanted to know how can we capture those, and our idea was we make infiltration experiments with tension filtrometers, and after this we wanted to assess how important are these differences that might occur, and that is why we made a water simulation with time variable soil hydraulic properties. So the objectives are pretty clear: quantification of temporal changes of hydraulic properties, then the implementation into a soil water model, and last but not least, a small model assessment with measured soil water data. Field experiments were carried out close to Vienna, in the eastern part of Austria. It's rather dry. The Austrians almost call it a little bit water limiting area. When I talk to people from Spain, Portugal, they don't agree with that. But anyway, we have a silty loam or sandy loam soil. It's a Chernocene, and you can see some properties here. And what was done is that it was cropped with windweed, and over 2 consecutive years we went out to the field and applied tension infiltrometer experiments on the surface. You can see the dates, and yeah, there was a tillage trial where we over a longer time period, since 15 years, these different techniques are applied. You all know conventional tillage, where the soil is plowed before seedbed preparation in spring, and then we have the so-called reduced or minimum tillage technique, where only this the seedbed is prepared, and we have this direct seeding technique, which hardly changes artificially the soil structure. Infiltration experiments were carried out with these soil moisture measurement system tension infiltrometers. We applied certain pressure steps, and these infiltration data were used to derive the unsaturated hydraulic conductivity using the method of wooding. And for the topsoil, which was we treated the first 20 centimeters as the topsoil. We know that the influence of this infiltration experiment is rather small. It's like 5, maybe 10 centimeters when you dig out the infiltration pattern at the end of the experiment. You will see that the influence of this experiment is rather small, but nevertheless we assume that we have a rather homogeneous property distribution in the topsoil layer, at least for the conventional plowed layer. This might be true. This data was used afterwards using Hydrus to inversely estimate the hydraulic properties of the standard Zangeluchten model. We made some simplifications. We used the Ks value that was derived by this wooding equation, and sorry, we did not fit. We did not feed the residual water content. Once we had derived the hydraulic properties like the alpha and n value, I have to admit that n is hardly sensitive to these near saturated infiltration experiments. But these data was used to derive a representative mean hydraulic property functions afterwards. This was done for each time of measurement. I showed you these 10 times where we made these measurements, and we also calculated a representative mean hydraulic property function for the entire infiltration tests. And the time course was described by just, and that's still what we are working on. It's still described just with a cubic spline that describes the change of the scaling factors. But later on, we want to use some more physically based models that describe these changes. Nevertheless, it's the time course of the hydraulic property changes is rather complicated. It's not that simple that we have, let's say, after a plowing event, that we have a strong increase in total porosity and saturated conductivity and a slight decrease afterwards, as we would assume it from existing model approaches. But it's a little bit more complicated, and we are currently working on this. The deeper soil layers were just treated as temporally constant. We took samples and derived hydraulic properties just once. Okay. The data was used to set up a model that allows us to simulate soil water dynamics over the 2 consecutive years. We used a program that is able to solve partial differential equations, to solve the Richards equations. It's constant multiphysics, and just as we would do it in Hydrus, we applied an upper boundary with a combination of precipitation and evaporation. Transpiration was implemented as a sinc term, just with this reduction function proposed by Fettis, and the lower boundary was a unit gradient, as there was no groundwater table present at this experimental site. So we made simulations over 2 years with a daily discretization, and we made for each of the different tillage types, we made simulations with temporally constant, meaning this representative mean hydraulic property function, and with time variables and hydraulic properties. And we were lucky that we had some measured soil water data at the field site. We had some probes installed, and this allowed us to somehow assess the quality of the simulation. First, let's have a look what we found out when we had a look at the hydraulic conductivity. This is a direct result of the infiltration tests. And what can be seen here, it's just the conductivity as a function of pressure head increasing to the left side. And it's what we found out is that under conventional tillage we found the highest conductivity. We found also strong temporal changes when you have a look at the different measurement sets. And the second line is the coefficient of variation, because we made 3 replicative measurements each time. And what can be seen here is that we also have a considerable spatial variability. And this was largest in the direct seeding plot, can be seen here for instance. And of course this is mainly due to the occurrence of macropores. And in this direct seeding technique, the soil is not changed artificially, so it's not so homogeneous as we find it in the conventional tillage. And the soil structure has some time to develop, and we found, this is not shown in this graph, but it's in the paper, we found that the connectivity of the pores are more, the connectivity is higher in the direct seeding treatment, and also the temporal stability of this pore system. Having a look at the inversely estimated parameters, we found that alpha showed also a strong temporal variability. It was opposite to the saturated conductivity that we found the largest values for direct seeding. As I mentioned before, N is hardly sensitive to these types of measurements. And I'll move on. Let's have a look at the results of the simulation. So we put all these parameters into the soil water simulation, and what can be seen here in this graph is these gray shaded areas. This is the mean and the standard variation to give some estimate of the variability of the measured soil water contents. We had probes installed, and of course they do not give the same value, but they have they result in different values as a result of spatial variability. So this was just to give you an idea of the range where the soil water content could be. And then we had a look at the simulation results. By the way, this is the water content in a depth of 10 centimeters, so 20, it's rather shallow. And the bottom one is the storage of water in the uppermost 30 centimeters. And you see these results for the different treatments. What can be seen from the gray shaded areas is that we have the smallest variability in measured water contents in the conventional treatment, which was expected due to this, what I mentioned before, this homogeneous properties. And when we have a look at these simulations, the first statement would be that the simulation fit quite well. Both simulations fit quite well to the measured data. And this means, yes, we can use inversely estimated hydraulic properties within some water simulations. It was not so much done before, and of course this allows us to rather simply and fastly get hydraulic properties from field experiments that can be used in saltwater simulations. And the second finding is that the quality or the quality of the simulation will be improved by using these time variable hydraulic properties. And this is also should be also shown in this on this slide. We made some quality assessments by using the root mean square error, and what was found is that we had a quite well reduction of the error between observed and simulated water contents for all three treatments that is seen here. Let's come to a conclusion. So I hope I could show that soil hydraulic properties are in fact not temporally constant, but they change as a result of soil tillage, but also other natural influence factors. We found that the conductivity also differed between the different tillage treatments, and that was observed by other studies as well. In our study, the conventional tillage led to the highest conductivity functions. And we could show that the direct seeding technique increases the temporal stability of the pore system, but also the connectivity of the near-saturated larger meso to macropore network. And our simulation could show two main things. That's my take-home message. First of all, yes, we can easily estimate hydraulic properties from inversely from field experiments that can be used for saltwater simulations. And the second thing is that the use of time variable hydraulic properties can improve the accuracy of saltwater simulations, especially in this highly variable shallow or uppermost soil layer. The perspective would be, I mentioned it before, we would like to come up with a better description of what was now described just with the cubic spline, what really physically happens. And there are some approaches like the pore size evolution model that was published by Danny Orr a couple of years ago. As I mentioned before, there are some difficulties due to the complex change of the pore system in reality. And another thing that might help us is to have a better or more comprehensive time series that would allow us to correlate changes that occur in the pore system with easily measurable properties. This could be done by state space models, for instance, when we have a time series. So this will be subject to future changes. If you're interested in this, you could have a look at this paper that presents the modeling approach and the general changes of the pore system as evaluated by the infiltration experiment was published here. So thank you for the audience, and if you have some questions, I'd be happy to answer.
I have a question. You did some of the simulations with console. You talked about daily discretization of 1 day. Does that mean you had the time steps of 1 day? Or what?
Yeah, that's the output. The time step can be smaller, of course, when we have larger precipitation events. Then the program automatically.
How did you feed in your weather data? Was that daily values or?
Yeah. Daily mean values.
I thought that you time average, so you did not time average that.
No.
Okay.
One question.
Yes, please.
You said alpha is the time variable, right?
Yes.
But did you measure the retention function for several times? What I mean is you fix L value. you use L equals 0.5 all the time. But my feeling is, if the conductivity is time variable, L might be the time variable. See, if the water retention property is almost same, you can keep the alpha constant and you allow L variable. Don't you think so?
I don't think I'm right.
Generally speaking, keeping L equals 0.5 is not a good idea. Generally, L is not 0.5. Don't you think so?
So once again.
See, many people still keep the L equals 0.5. But when you measure the conductivity, L is not usually 0.5.
That's definitely an issue. There are some simplifications that we
but
had
what I
to.
mean is, the third can be changed. The conductivity can change, but the retention data might be not so changed. Don't you think so?
Yeah, that's true. But you have a closed form equation, and when you change, when changes.
You estimate,
Sorry?
You estimate